We apply this encryption function upon all the letters of this message after converting them to capital letters. So the first step, we convert the letters in the message to capital letters, and then for each letter we apply this function f of a. Okay. Remember that we can change this function if we want to encrypt using a different function, but this function has to stay invertible. Alright, so when we use this function, then the letter S mapped, which represents the numerical letter 19, gets mapped to 14, as we have seen in this step, which represents the letter of the English alphabet N, as we can see from the table here. So S, by using this function, gets mapped to N. So in the encrypted message, instead of sending S, we can transmit N, and hopefully no one will be able to figure out the reverse transformation. Similarly, the letter T, which represents the numerical letter 20, if we go back in the table and see, so T represents 20. By using this function, is transformed to number 17, which by using this table represents the letter Q. We apply this process on all the letters in the alphabet, and we see that this message stop thief is transformed to something which may appear gibberish to a person who does not know this function, and they may not be able to understand the message being sent. Again, this is a very simple example, and if we decide to transmit long messages by using these encryption functions, then someone may figure out very easily that this is the function we are using. So the modern ciphers use more sophisticated functions and other strategies to enhance the quality of encryption or the resistance of the encryption to attacks. But the underlying principle is that the transformation must be invertible and must be difficult for the outsiders to guess. This brings us to the conclusion of this chapter number 4. I hope that you enjoyed this lecture and learned the basics of number theory.